Hey everyone, so good evening. I wanted to show you something interesting that I learned today. This is Euler's method. Now this is a very simplified method, a simplified way of using Euler's method, but it's basically using iterations, multiple iterations to approximate a value if you can't say solve for an equation analytically. Alright, so first off, let me just show you what we're working with here. We've got the equation for an oscillation, which is acceleration equals to radians angular velocity squared multiplied by displacement. Okay, and basically in this case you don't know what the equation for displacement is, but you know two things, right? That the displacement is approximately, the displacement after some time t is approximately the old displacement followed by the new displacement, like the displacement in a very small amount of time. And in this small amount of time, what you're assuming is that the acceleration remains unchanged. But in truth, in reality, the acceleration is constantly changing. So you can't actually predict it with 100% certainty. So that's why we call it an approximation. And basically, for the smaller values of epsilon you use, the more accurate of a value you're going to receive for your change in displacement. Right. So first off, this is the analytical equation for displacement. But as you can see, compared to this, we don't have to solve the equation analytically. Okay, what that means is that we don't have to use calculus and integration to solve it like some kind of puzzle. Computers don't do that. Computers do multiple iterations. Right, so let's see how it works, how Euler's method works in a very simplified way. So first what you want to do is you want to compute time equals 0. You want to compute what actually happens when time equals 0, because you see the O velocity plus the small increment in time elapsed is going to give you the new velocity, right? See, t plus epsilon, where epsilon is a very small time after that period. So you're assuming acceleration doesn't change, okay? And then you compute it, right? And obviously you have to know the initial displacement, the initial velocity at time equals 0, and you also have to know the angular velocity of your equation. Otherwise, you're not going to be able to solve this. All right, but it's way easier than calculating everything analytically. So you compute it, you plug in your O velocity. I mean, you plug in your initial displacement at t equals 0, followed by your angular velocity. There you go, boom. You're gonna get your acceleration. Okay. Afterwards, you plug in your acceleration. After that, you plug in your acceleration, and you're gonna see how your acceleration affects that small interval of time. It's going to boom bang. It's going to reduce it by 0.1 meters per second. Okay. Initially, your velocity was 0, but it's gonna make it 0.1 meters per second, right? Because it's 0 plus 0.1 times negative 10, so you get. This is your new velocity, basically, because the time elapsed, like I said, we're assuming that acceleration doesn't change. And then you do the exact same thing for your displacement, and boom, you got your new displacement. And what you want to do now is you want to plug this back into here. So your acceleration is going to constantly changing with your displacement. See, your acceleration is going to constantly change with displacement, and then you're going to get a new acceleration, and you're going to repeat the whole process. You can repeat it 100 more times. Since we're using epsilon as 0.01 seconds for an accurate value, you're going to need to repeat this 100 times just to find out what the position is at 1 second. And it's only going to be an approximation. If you're going to get a better approximation, you have to add more zeros. All right, you have to add more orders of magnitude behind. And basically, this is what computers do. Okay, this is what computers do in a very simplified way. They do this for lots of equations because it's impossible to calculate the air resistance analytically, or rather it's super difficult. We just don't have the technology, and it's just this brute force of equation. One great historical example of them doing this, one great historical example of people using this before computers were really prominent is Katherine Johnson, right? She was part of NASA, and then she computed the trajectory of the rockets for the Apollo mission astronauts using Euler's method. She had to, just imagine, they had to go through this like 1,000 times just to get really accurate values because they didn't have computers back then. Alright, so that's really cool. Some history for you. But now, currently in the present, obviously, we don't have to rely so much on laborious methods. We can just plug it into a computer. Computer's going to do all the labor for us. It's going to obviously take up lots of electricity, but so what? It saves us lots more on labor. Yeah, so interesting video for you guys. This is how Euler's method works in a very simplified way. Enjoy.